Hello, class. Hello, class. Today we're going to do section 3.4, Piecewise Defined Functions and Absolute Value Functions. Our objectives today are to evaluate and graph piecewise defined functions, graph the greatest integer function, graph the absolute value function, and solve absolute value equations. Now, sometimes a function is defined in pieces for different intervals of the domain. This will be a piecewise function. Let's look at an example. This example is a postage example. It says the postage paid for a first class letter jumps by 15 cents for each ounce after the first ounce, but does not increase until the weight increases by 1 ounce. The table gives the postage for letters up to 3.5 ounces. Write a piecewise defined function that models the price of the postage and graph the function. All right, so here's the table over here to the right hand side. For weight X in ounces, from 0 all the way to 1, the postage is going to cost 55 cents. From 1 all the way to 2, the postage is going to cost 70 cents. From 2 all the way to 3, the postage will cost 85 cents. And from 3 all the way to 3.5, the postage will cost 100 cents. Keep in mind, you could tell that there's some repeats in numbers here, but like for instance here, if it's equal exactly to 1 ounce, it'll be 55 cents. It won't be 70 cents. If it's equal to exactly 2 ounces, it'll be 70 cents. It won't be 85 cents, and so on. Now, the way that we write this function is we define the function by p of x. So we write p of x equals, and we'll use this fancy little curly Q bracket right here. And we write out each of the possibilities, each of the pieces. So the first piece is 55 if 0 is less than x is less than or equal to 1. 70 if 1 is less than x is less than or equal to 2. 85 if 2 is less than x is less than or equal to 3. 100 if 3 is less than x is less than or equal to 3.5. So basically defining each and every piece that we are given. Okay, you notice that each piece is defined on its individual domain, and that has to be given as well. Let's look at how the graph would look. Sometimes they call these step functions because the graphs sometimes look like steps depending on how the function is defined. So you'll notice on the graph we use open circles to describe areas where it's not equal to and closed circles where it is equal to. So on this first one, it's got an open circle on 0 because we obviously can't mail something that doesn't weigh anything. It's got to weigh something. So open circle on 0, but all the way to a closed circle on 1. That line lines on 55, and then we go up to 70, and then we go up to 85, and then we go up to 100. Okay, so this defines your p of x function. Notice that each of these lines are representing the cent value only on their respective domains. Okay, that's the biggest thing with piecewise functions. We only graph on the respected domains. So let's look at another one. This one says f of x equals 5x plus 2. If 0 is less than or equal to x is less than 3. And x to the third power if 3 is less than or equal to x is less than or equal to 5. Okay. Now with one like this, what we're going to have to do is we're essentially going to have to graph the two separate pieces. Okay, on their respective domain. The first domain here is from 0 to 3. So if I'm looking at 5x plus 2, I want to graph this on the domain from 0 to 3. Now 5x plus 2 is linear, so I really only need 2 points to graph it. So if I plug in 0, I can see that 5 times 0 is 0, plus 2 is 2. So I should have the point 0, 2 that I need to graph. And if I plug in the other endpoint of 3, 5 times 3 is 15. 15 plus 2 is 17. I should have the other point 3, 17. Okay, and you'll notice that you could plug in several points. The most important points here, especially since that particular part of the piecewise defined function is just a line, are the endpoints. Okay, now we're never going to be equal to 3, so we need to draw an open circle on that 317 point. But let's look at the cubic function. Now the cubic function isn't a straight line, so we definitely need more than 2 points. Okay, I'm going to start with the endpoints. I'm going to plug in a 3. So 3 to the third power is 27. And then I'm going to plug in the other endpoint of 5. 5 to the third power is 125. So I should have the points 327 and 5, 125. I need to plug in at least one more point because it's a cubic function. I need at least 3 points for it. So if I plug in 4 to the third power, 4 to the third power is 64. now I have 3 points to graph on it. So if I come over here to the graph and actually graph the function, I need to plot them just on their respective domains. Okay, so from 0 to 3, I'm going to plot this 5x plus 2. Okay, so remember that first point here was 0, 2. So that's where the first point is. And the second point here was 317, but it's not equal there because it doesn't have an equal to sign here. So I have to use an open circle. Now, from this point, I can move over to the cubic function. Now, it is equal to 3 on the cubic function, so I'll put a solid dot. Remember, 3 cubed here was 27, and then it curves on up all the way to that point that we found of 525. So if I was sketching it by hand, I'd definitely plot the 464 as well to help me with that curvature of that line. All right, let's look at another example, wind chill factor. Wind chill factors are used to measure the effect of the combination of temperature and wind speed on human comfort by providing equivalent air temperatures with no wind blowing. One formula that gives wind chill factor for a 30-degree Fahrenheit temperature and a wind velocity v in miles per hour is W equals 30 if 0 is less than or equal to v is less than 4. W equals 1.259 v minus 18.611 times the square root of v plus 62.255 if 4 is less than or equal to v is less than or equal to 55.9. And W equals negative 6.5 if v is greater than 55.9. Okay, so we have it broken into 3 pieces here. Now let's find the wind chill factor for 30 degrees Fahrenheit temperature if the wind is 40 miles an hour. All right, so if v equals 40, which domain do I lie in? Well, I don't lie 0 to 4, and I definitely 40 is not bigger than 55.9. So if v is bigger than 40, I need to use this formula and figure out what w is, because this is where v lies. Okay, 40 lies within this domain between 4 and 55.9. So I will plug 40 into that formula, and if I do that, and you can do that on your TI. Take some time to type it in. Make sure you can type this in on your TI and get the correct answer. Gives you approximately negative 5.091 or approximately negative 5. Okay. Let's look at part B. It says find the wind chill factor for 30 degrees Fahrenheit temperature if the wind is 65 miles per hour. Okay. Now 65. So let's see. Let's look at it in a different color here. So if V is now 65. Where's 65 live? Well, it's not in 0 to 4. It's not 4 to 55.9. If it's 65, it's living here. So if the wind is at 65 miles an hour, then it looks like our wind chill factor is going to be at negative 6.5. Okay. So because V is 65 is in the interval where V is greater than 55.9, the wind chill factor is negative 6.5. Don't even have to solve for anything there because it doesn't have a variable to solve for on there. It just straight is that number. That means if the wind is 65 miles an hour, a temperature of 30 degrees Fahrenheit would feel like negative 6.5 degrees Fahrenheit. Now, if we graph the function over the interval from 0 to 70, then we have to graph each of the individual pieces. Okay, you'll notice here this first piece, where W equals 30, is graphed from 0 to 4. So basically here to about there. And you can see that it's a straight line just at 30. Then we get into the 1.259v minus 18.611 times the square root of v plus 62.255. That's this curvature, and it lasts from 4 all the way to 55.9, so maybe about right here. And then we transition into negative 6.5, so it goes from a curvature down to literally a straight line once again after that point. Okay, so that piece is made up of 3 functions itself. If you notice here, we don't have any open or closed circles because we don't really have any discontinuities here. Let's also now look at the absolute value equation. It says if the absolute value of x equals a, and a is greater than 0, then x equals a or x equals negative a. There is no solution to the absolute value of x equals a if a is less than 0. And absolute value of x equals 0 has the solution of x equals 0. Okay. Essentially, These vertical lines that surround the x here, that's the absolute value. That's how we represent it. I can take the absolute value of a positive number, a negative number, or 0. The only thing I can't do is I can't find the absolute value of a number and it turn out to be a negative number. So in this case, say -4. I can't do this. Okay, but I can take the absolute value of -4 because the absolute value of -4 is +4. Okay, absolute value is always positive because absolute value is measuring the distance from 0, and distance can technically never be negative. Distance can have direction, but it can't really have a negative measure. So let's look at solving some of these equations. So A says the absolute value of x minus 3 equals 9. Okay, now this is kind of similar to what we do with square roots here. Essentially, if I want to drop off this absolute value, I need to consider the positive and negative aspect. Okay, so x minus 3 equals plus or minus 9 is how I'm able to drop that absolute value off. The logic behind that is that if I take the absolute value of 9, so if I get x minus 3 to be 9, if I take the absolute value of 9, it's going to give me the answer of 9. If I get x minus 3 to be -9, and I take the absolute value of -9, that's also going to give me 9. So I can get rid of this absolute value by breaking it up into two cases of positive and -9 because the absolute value of either positive or -9 is 9. Okay, so we break it into these two circumstances here. X minus 3 equals 9 and x minus 3 equals -9. I add 3 to the other side in both equations. And I see that x has to either be 12 or x has to be -6. Which makes sense because 12 minus 3 is 9. The absolute value of 9 is 9. And -6 minus 3 is -9. The absolute value of -9 is 9. Let's look at B. Now B is the absolute value of 2x minus 4 equals 8. If I want to drop off that absolute value, I'll just say 2x minus 4 equals plus or minus 8. I'm going to break it up into the positive and negative function just like I do down here at B. And I'm going to say 2x minus 4 equals 8 or 2x minus 4 equals -8. In both of them, I'm just adding 4 to the other side. Okay. If I add 4 to the other side, I get 2x equals 12 or 2x equals -4. If I divide by 2 to get x by itself, then I'm going to see that x equals 6 or x equals -2. So there's my two solutions there. You don't have to solve them at the same time. You can solve them individually. You should still get x equals 2 or x equals x equals 6 or x equals -2. Now let's do a little more complicated one here. Here I have the absolute value of x squared minus 5x equals 6. So if I was going to break this one up, it would look like x squared minus 5x equals plus or minus 6. Okay. Now that breaks, like I said, down into two equations. Here I have x squared minus 5x equals 6. And here I have x squared minus 5x equals -6. Okay. I'm going to solve this one over here on the left first, and then we'll go back and solve the one on the right. Okay. All I'm doing to start with is subtracting the 6 over, getting everything on one side, so that I can take this quadratic, factor it, and then solve. Okay. So I get x squared minus 5x minus 6 equals 0. I factor that into x minus 6 times x plus 1 equals 0. I'm going to break both of those factors up and set them equal to 0. So x minus 6 equals 0, x plus 1 equals 0. Oops. Erase here. So here we see that x is 6 and x is -1. Okay. Same solutions that we have right here. Now on the other side, I'm going to add 6 to the other side. Get everything all on one side, same thing, so I can factor. So I have x squared minus 5x plus 6 equals 0. That should factor into x minus 3 times x minus 2. I'm going to set x minus 3 equal to 0. I'm going to set x minus 2 equal to 0. So we can see that x equals 3 and x equals 2 are both solutions. So we have, for this absolute value quadratic equation here, we actually have 4 solutions. And all of those solutions will actually render you a correct answer. So you don't have to have just 2 solutions. You could have 1 solution, you could have 2 solutions, you could have quite a few different solutions depending on how big your equation is here that you've mixed your absolute value in with. If you have any questions, reach out to me. This concludes the chapter 3 lectures for us. Go on, try your homework. Like I said, if you have any problems or issues, let me know. Reach out to me. And other than that, I will see y'all next time.